Assalamu alaikum. This is lecture 5 on modern control theory. We are discussing solution of the state equation. In the last class, we have seen the Laplace transform solution of the state equation. Today, we are going to see the solution of the state equation in the time domain. So basically, so article 4.1. Also, we have to go to the appendix J to derive the theorem. So let's start. So in the beginning, we'll start with the homogeneous equation. Basically, our state equation is xt. One thing I forgot to tell you is that all of these parameters are actually either vector or matrix. So once we actually represent vector or matrix, we in general have to give a bold letter. We have to use a bold letter whenever we are trying to write in the inside documents. But here is not possible. So that is why this ideally we should have been given a line under the each character. So A and B is matrix, and X dot is in general a vector, a state vector, derivative of state vector, but it can also have multiple rows and columns depending on your states arrangement. So this is the scenario, and also we can have MIMO system, multiple input, multiple output. So bottom line is somehow we are avoiding these the lines under the characters, but you always remember these are either vectors or matrix, like A and B are matrix, and X dot, X, T, and UT are actually vector. So at the very beginning, start with the homogeneous equation. So assume homogeneous equation, state equation obviously. It is homogeneous state equation. Homogeneous means actually unforced, basically, or zero input. So basically, you're just avoiding the second term. So initially, let us just solve this portion of the equation. Then with the help of the properties that we're going to obtain from this one, we're going to introduce the forced or non-homogeneous part of it. Okay, so say x dot t equal to axt. Now we assume that the solution will have a series of pattern, and we assume that xt is, this is our say equation 1, and xt is having a series something like this: b dot coefficients b1t plus b2 p square plus goes on up to bk tk plus b k plus 1 t k plus 1 and goes on. So basically infinite series solution for xt. Now we place so this is our equation 2. So now what we can do is we can take a substitution of this xt, that means the solution. So we place this x into this equation. Let's see how it turns out. So basically what it will be B1, because if you uh, differentiate the x, then what we are going to have is the first term is a constant, so it will be vanished. And second term, the t will be vanished, so B1 will be vanished. So B1 plus, because of the squared term, 2 will be coming forward, so 2B2 t plus goes on up to k bk k minus 1 will be reduced because of the differentiation, and then plus k plus 1 b k plus 1 t to the power k, and goes on. So this will be the left side, and the right side will have a common. Then we'll have the matrix b0 plus b1 t plus b2 t squared goes on to bk t to the power k plus b k plus 1 t to the power k plus 1 plus goes on. Okay, now in the both sides, the coefficients, the like coefficients, we have to equate. So equating like coefficients. That means the coefficients of t in the both side, the constants in the both side, the coefficient of t square in the both side, the coefficient of tk in the both side. Okay, so this is what we have to equate. Now that will give us the first parameter b1 will be actually a into b0, this one, a into b0. Then the second parameter will be basically 2b2 should be equal to a into b1. So 2b2 equal to 2b2 equal to a into b1. So if you take 2 in the other side, we'll have something like this. b2 equal to half a b1. Now again we can replace the value of the b1. So if you replace the value of the b1 into this equation, then half, then we have a square b0. So as you can see here, the first parameter is 1. So based on that, you have a magnitude of 1 here, and you have a power of a is 1 as well. Second parameter is 2, and so you have 2 here. So you have a square there. So if you continue the series, so it will be basically bk equal to 1 by k factorial ak and b0 initial value. Okay, so also similarly, b k plus 1 should be equal to 1 by k plus 1 factorial and a k plus 1 b0. Okay, now in the equation 2, that is our solution of x, that is this one. So in equation 2, if we replace the values of all the coefficients, b0 is already there, so b1, b2, and let's see how it turns out. So substituting into gives us xt equal to b0 plus a b0t plus half a square b0 t square plus goes on 1 by k factorial ak b0 tk plus 1 by k plus 1 factorial a k plus 1 b0 t k plus 1. Okay, so now in this equation, what we can find is we can see that b0 is common throughout the equation, so you can just take a common of that thing. And then what will be left is, since all of them are actually the vector parameters, so if you take common of b0 from the first one, so identity matrix will be there, plus then you have a t plus half a square t square plus goes on to 1 by factorial k ak tk plus 1 by k plus 1 factorial a k plus 1 t k plus 1 plus goes on. So you can just take the common of b0. Now, from this equation, we can also see that if also from equation 2, whatever which one you want to take, if you take x at t equal to 0, then as you can see, the rest of the parameter is vanishing. So x0 will be actually only b0. So we can replace this one. So that will give us something like this. I plus at plus half a squared t squared plus 1 by factorial k ak tk plus 1 by k plus 1 factorial a k plus 1 tk plus 1 plus goes on. Then we can say this is our actually x0. Okay. Okay, now this parameter here, this is something similar to if you have expanding, if you are expanding e to the power 80. Okay, so if you expand e to the power 80 as a series, we can actually find a 1 plus 80 plus half a square t square plus goes on plus 1 by k factorial ak tk plus 1 by k plus 1 factorial a k plus 1 t k plus 1 goes on. So this is a series. So actually, based on this idea, even though the parameter a here and capital A is not same, capital A is a system matrix. Okay, so but we can take the same notation. So we can replace this one by the same identity to the power a. Okay, so what we'll have now is basically finally xt equal to e to the power a t, then you have x0. Okay, so as I already said, some of them are vectors, some of them are matrix, so we have to give the underline. So in the throughout the derivation, we will not actually use something like this. Rather, we'll be using this thing later. Now, this new parameter that we have, that is e to the power 80. Okay, so this is what is called state transition matrix. So this is what is called state transition matrix. The reason for calling this one state transition matrix is we are starting from state 0, and through this matrix we are actually obtaining the any later value of state xt. So that is why It is called state transition matrix that will actually help you to go from state 0 to some future time xt. Okay, so also xt is e to the power at is also denoted as phi t, capital phi t, equal to e to the power at. Okay. So what we can finally write is xt is equal to phi t, then you have x0. Okay, so let us try to find out some of the properties of this equation. So let's say this is your equation 3. I think we just use 2. So say this is equation 3. Now, the first property is say at t, what happens at t equal to 0. So at t equal to 0, you can see that x0 equal to phi 0 and x0. Since they're all matrix or vector, they basically, if you take the common thing you can take from each side, you can say that identity matrix equal to phi 0. Okay, so this is basically our first property. The state transition matrix at the beginning or at t equal to 0 is equal to identity matrix. So first property that we can use later on. Now, second property, again from that equation, that x dot t equal to, okay, so the equation 3, we are actually differentiating equation 3 gives us x dot t equal to phi dot t, and since the initial condition that will not change, so that will be remaining as it is. Okay. Now again, from the first equation, we also know to the fact that from the homogeneous equation, this is also equal to a xt. Okay, so if we take at t equal to 0, what will be happening to this equation? Basically, this two is phi dot 0 equal to x0 into x0 equal to a x0. So x0 can be cancelled out. So the differentiation of the state transition matrix, and if setting it to time 0, will give you the system matrix A. So this is our second property. Okay, so while solving the math problems, we have to use these two assumptions, these two properties. Okay, so now, so far what we have figured out is the summary of the homogeneous solution is xt equal to phi t x0, and where we have few properties where phi 0 is actually identity matrix and phi dot 0 is actually our system matrix. So this is the summary so far. Now let us go for the forced or non-homogeneous problem. Okay, so forced or non-homogeneous state equation. Basically, x dot t equal to a xt. Now you're just adding the input portion of it. Okay, so first thing that we can do is rearranging a bit, and that will taking the x into one side, x dot t minus a x t equal to b u t. Now we have our solution. Okay. Now multiplying both sides with multiplying both sides with e to the power minus 80. So this will give us something like this, e to the power minus a t x dot t minus a x t equal to e to the power minus a t b u t. Now, on the left side, if you just see that, can we have a form like this? So, different time derivative of e to the power minus a t x t. So, what is the time derivative of this one? Let's try to figure out. So, if you find out the time derivative of this one, then we are going to see that it will give you if you take the first parameter as a constant, then it will be minus at, then x dot t. And if you take now this one constant, then it will give you xt minus a will be there, and also e to the minus 80. So as you can see, if you rearrange e to the minus 80, you can take common, then x dot t minus a xt. So which is same as the left side. So we can write that d by, you can write the left side as d by dt of e to the power minus at xt equal to e to the power minus at b ut. Okay, so now if we integrate both sides, so integrating will provide us both sides will give us something like with a range of 0 to t, of course. So now it will give us the left side, whatever the solution we already have, you just have to put the limit, that is 0 and t. In the right side, integration 0 to t with the limit e to the power minus a tau b u tau and d tau. Okay. So simplifying the left side will give us t. If you put the t there, it will be simply as it is, e to the power minus at the xt. Then it will be minus 80. If you put 0, it will be 0, so it will be x0 equal to integration in the other side, that is 0 to t e to the power minus a tau. Tau is just an integrating operator because our final value is t, so we cannot say the same t while we're doing the integration. So that is why we're just integrating operator as tau is being introduced, u tau d tau. Okay, so you take x0 into the other side, so it is minus a t xt equal to x0 plus integration So now we can take e to the power minus a2 into the other side. That will give us something like this: x t equal to minus 80 will be going to plus 80. So it will be plus 80 x0. Then integration plus 0 to 2 e to the power minus a tau. Then you have e to the power a t. Then you have b u tau d tau. So xt is the other parameters are remaining same. Now we can actually rewrite rewrite this thing as e to the power minus a. Okay, sorry, it will plus t will be coming first. So now also it will be wiser to not define this one as well, because these are matrix quantities. So changing the order is not a wise thing to do. So 80 minus a tau. So if we take common, then we have a t minus tau p u tau d tau. Okay, so what we can write finally is this is nothing but our phi t as we defined earlier. So state transition matrix, and this is actually a shifted version of time delayed version of your state transition matrix. So if we can say this is as phi t, then we can say this one as phi t minus tau. So we can write our final equation. The solution basically is xt equal to phi t x0 plus 0 to t phi t minus tau b u tau d tau. So this is our solution. Now it has two parts. The first part is we have to be a bit patient about the definition of this one. So the first part is because of the state vector. So the first part is coming because of the state vector. So this one is known as, and it doesn't depend on the input. So that is why this portion, the first portion, is known as zero input response. Zero input response. Okay, so only term it depends on the initial state value, not on the input. Okay, so that is why it is called zero input response. Now, second part is basically it is because of your input, but initial state or zero state is missing. So that is why it is also called zero state response. Okay, so but according to my understanding, it would have been better. It would have been really better if we can say it state zero response. But I think they used the same ideology starting with the zero. That is why they kept it zero state response. But to me, it would have been really better if we could have said that it is a state zero response. But don't worry. So now this one depends on only x0, whereas this one depends on basically your B matrix, then your input. Okay, so but it doesn't depend on So, but not on x0. Whereas this one depends on x0, but not on your b or u or even the output y. So it doesn't depend on any one of them. Okay, so this is the scenario. And this is also, if you from the integral, you can see that this integral is also known as convolution integral, most probably in signals and systems or this digital signal processing. We have gone through this one. So convolution integral. Okay, so now what is the difference between this solution of this state equation with the solution of differential equation? So in general, we go through the solution of the differential equation. Okay, so what is the difference? The first difference is in the differential solution of the differential equation, we find two terms. One is called forced and the other one is called natural response. Natural response. So those two are not present definitely in this two, zero input or zero step response. We cannot find them outwardly in the equation. So this is the first difference. And the second difference is once we are actually calculating the state response, the natural response in differential equation form, we have seen that natural response depend on your initial value, as well as the derivatives, initial value of the input or initial value of the output, as well as their differentiation, derivatives of your u and y. So, and their corresponding initial values as well. But this thing is not same as the two responses that we're getting from the state solution of the state equation. So this one only depends on x0, this one depends on only input. So that is kind of different. Now, before going to the math problem, the math problem will make things a lot easier to understand what is happening. You have to figure out something as well. So how can I actually calculate the phi? Okay, so let us try to figure out an alternative approach of figuring the state transition matrix, that is phi t. How can we calculate phi t in an alternative way? So we know that from the last chapter that XS is something like this, SI minus A inverse matrix of this one into X0. Then we have SI minus A inverse B US. Okay, so this is already know from the chapter 4, chapter 3, while we are actually transferring the state equation into the transfer function. Okay, so now also as you can see, this is the part that only depends on x0, and this is the part that only depends on this value. Now, if we can just say the Laplace transformation of your xt. Okay, so and also you know the equation is the homogeneous equation that we have is xt equal to the solution of the homogeneous equation is this one, x0. Now, if you take the Laplace transformation of the homogeneous equation, then it will give us something like this. Okay, so this is same as this part. So basically, This will be your SI minus A inverse with your X0. So X0 is common, so you can say that Laplace transformation of your phi t, that is state transition matrix, is equal to the ASI minus A inverse. So, or inversely, we can say that if you take inverse Laplace transformation of the matrix SI minus A, then also we can find out the phi t. Okay, so and also the inverse matrix. So this is the alternative way to figure out the state transition matrix. But one point we want to figure out is that the inverse matrices can be actually written as adjacent SI minus A divided by determinant of SI minus A. So now what we are actually trying to say is that the determinant is present in each parameter of your phi. And what is determinant? Determinant is nothing but the poles of the system. So poles of the system, and which means it actually have the exponential of the system response. So all the poles of the system is actually will be included in phi t. So if you have a two-order phi t, then you will have something like this. Say you have two poles here at S1 and S2, and you have a state matrix like this, phi t. So all four of them will actually have a combination of these two, like say K1 e to the power minus S1t plus K2 e to the power minus S2t. Then this one is also K3 e to the power minus S1t plus K4 e to the power minus S2t. So K5 e to the power minus S1t plus K6 a to the power minus S2t, K7 e to the power minus S1t plus K8 e to the power minus S2t. So all the parameter, this parameter, this parameter, this parameter, all of them are actually having the exponentials. So just our task is to find out what is the value of K1 through K8 using the two identity that we have used, derived, that is phi 0 equal to I and phi dot 0 equal to A. So this is one way, or alternatively using the inverse matrix, we can also directly calculate phi. So now everything been derived, let us now try to solve the problem. Two problems we are going to solve. Now let us start with the first one. Example 4.12. 4.12. So basically xt is x dot t equal to 0, 1, minus 8, minus 6, xt plus 0, 1, that is B matrix, ut, and then zero condition is also given, equal to 1 and 0. So these are the things given. We have to calculate the value of the state, the solution of the state equation. So let us start. So we know that x dot t equal to a xt plus b ut. Now, first of all, let us find out the the matrix, find out the poles of the system. So the poles are nothing but the eigenvalues, or basically the determinant of Si minus A. So Si minus A, we have to figure out first. So S1001 minus, we have 01 minus 8 minus 6. So basically S minus 1, 8, S plus 6. Okay, so now find out the determinant to find out the eigenvalue of the poles. So determinant of Si minus A equal to basically S into S plus 6 plus 8. So S square plus 6, 8 plus 8, which eventually is nothing but S plus 2 into S plus 4. So we can say that S12 is nothing but minus 2 and minus 4. So as we said that the state matrix, state transition matrix, that is phi t, will actually have always these exponents. So we can say that this will be k1 e to the power minus twice t plus k2 e to the power minus 4t. Similarly, k3 e to the power minus twice t plus k4 e to the power minus 4t, k5 e to the power minus twice t plus k6 e to the power minus 4t, k7 e to the power minus twice t plus k8 e to the power minus 4t. Okay, so now we have to use those two conditions. The first condition is phi 0 equal to identity matrix, that is 1, 0, 0, 1. Okay, and the other condition is phi dot 0 equal to A, that is 0, 1, minus 8, minus 6. So from this one, if you plug into these values, so the first value is simply just replace the time with 0. So what you can say is k1 plus k2 will be equal to 0. Then you have k3 plus k4 will be equal to, sorry, the first range has to be 1. 1, 0. Then k5 plus k6 equal to 0. And k7 plus k8 has to be equal to 1. Now the second one, we have to actually take the derivative of phi with respect to t, then we have to set t equal to 0. Okay, so as you can see, if you take derivative, minus 2 will be just coming forward here. Okay, minus 4 will be coming forward here. So what we are going to get is, and then the exponents will be vanished because t equal to 0. So what you can find is minus 2 k1 minus 4 k2 will be equal to 0, this one. Now from this one as well, same thing will be happening. Minus 2 k3 minus 4 k4 will be equal to 1. Similarly, minus 2 k5 minus 4 k6 will be equal to minus 8. Minus 2 k7 minus 4 k8 will be equal to minus 6. Now you have two equations. So this one and this one, and two unknowns. So you can easily solve this one, and this one will give the values of k3 and k4. Similarly, this one and this one, this one and this one. Eventually, what let me just write it. I think we'll be able to solve it very easily. So you can say that k1 is basically, k1 will be 2, and k2 is minus 1. Then K3 is half, and K4 equal to minus half. Then you have K5 equal to minus 4, K6 equal to 4, K7 equal to minus 1, and K8 equal to minus 2. So if you replace these values, then you can find our state transition matrix, that is phi t equal to 2 e to the power minus twice t minus 4 e to the power minus 4t half e to the power minus twice t minus half e to the power minus 4t. Then you have minus 4 e to the power minus twice t plus 4 e to the power minus 4t. And then you have minus e to the power minus twice t plus 2 e to the power minus 4t. Okay, so what was our solution? Our solution was basically xt was equal to phi t x 0 as well as plus integration of 0 to t phi t minus tau b u tau d tau. Okay, so phi already we figured out. We can also find out phi t minus tau. Basically, all the values here, t will be replaced by t minus tau. So additional minus t and tau will be added there. So this parameter is available. So now figure out the second term first. So what was our value? What was the value of the b? B was 0, 1. So we can say that phi t minus phi t minus tau b equal to phi, whatever we had, phi with a delayed version of course, and that phi into b equal to 0 and 1. So basically you have two parameters here, so this one, this one, this one, this one. So 0 will be multiplied with this one, so this one will vanish. We only have this parameter. Again, in the second line, this one will be vanished, so we will have this parameter. So basically we'll keep this one and this one. So, of course, the delay. So don't forget about the delay. So what we can write here is half e to the power minus 2 t minus tau minus half e to the power minus 4 t minus tau and minus 2. Okay, so minus e to the power twice t minus tau t minus tau, then plus 2 e to the power minus 4 t minus tau. I'm just keeping one line, so you just write that line and then it will be easier. Okay, now next thing is we can also find out the state phi t into x0. So phi t we already calculated, and then x0 is 0, sorry, 1, 0. So 1, 0. So again, if you have two parameters, now this parameter will be kept and this will be vanished because the second parameter is multiplied by 0. So what we have is first parameter only will be leaving. So 2 e to the power minus twice t minus e to the power minus 4t and minus 4 e to the power minus twice t plus 4 e to the power minus 4t. Okay, so again, we have to, this is the zero input response, zero input response. Whether you have noticed or not, zero input response has both the natural responses. So as you can see, the natural response is actually throughout the zero input response as well as zero state response. So let us finish the zero step response because we haven't done the integration. So let us do the integration. So now next thing that we should be doing is here we have to do the integration from 0 to t with phi t minus tau into b, then you have u tau d tau. Okay, so u can easily be used as the step response you can take. So basically then it will be magnitude will be 1, so you don't have to bother about that one. So you just integrating this one will give you the solution. So what we'll have is half e to the power minus twice t. T is a constant here because we are integrating with respect to tau. So 0 to tau e to the power twice tau d tau. Okay. So, and the second parameter is minus half e to the power minus 4t, then 0 to t e to the power 4 tau d tau. Similarly, in the second term, minus e to the power minus twice t, 0 to t e to the power twice tau d tau plus 2 e to the power minus 4 t, 0 to t e to the power 4 tau d tau. Okay, so the integration will give us something like this: half e to the power minus twice t, then it will be basically e to the power twice tau by 2, then 0 to t minus half e to the power minus 4t e to the power 4 tau by 4, 0 to t, and then minus e to the power twice t e to the power twice tau by 2 with 0 to t plus 2 e to the power minus 4t e to the power 4 tau by 4, 0 to t. Okay, so now if we find out, replace the values, then what will you have? Half e to the power minus twice t into e to the power twice t by 2 minus half, then minus half e to the power minus 4t e to the power 4t by 4 minus 1 by 4, and the second one minus e to the power twice t e to the power twice t by 2 minus half plus 2 e to the power minus 4t e to the power 4t by 4 minus half. Okay, so as we are approaching to the final, so now we can say that what we have here is this one, and this one actually will be canceling each other. So what we'll have is 1 by 4 minus half e to the power minus twice t. Then again this one and this one will cancelling each other. You multiply, then minus. Okay, so 1 by 8 minus 1 by 4 e to the power minus 40. So in the second one, minus half will be coming, then minus plus half e to the power minus twice t. Then you have plus 2 into 4, so basically half will be coming again, 1 by half. Then you will have half minus half e to the power minus 40. So as you can see, this one and this one getting cancelled out, and if we subtract 1 by 8 from 1 by 4, we'll be leaving with 1 by 8. So what we are going to see is 1 by 8 minus half e to the power minus twice t. I'm sorry, 1 by 4, because actually half and half will be multiplied. So 1 by 4, then minus 1 by 8. This one is also 1 by 8, because 2 is multiplied with 4, so it will be 8. So e to the power minus 4t. And then we have in the denominator half e to the power minus twice t minus half e to the power minus 4t. Okay, so this is your zero state response. Zero state response. Okay, so whether you have noticed or not, it has both your forced response. This is forced response, and these are actually components of your natural response. But the thing is that the coefficients here, so these coefficients, they, in the previous case, in the differential equation, they are actually obtained from the initial condition, but these are not dependent on initial condition. Okay, so as we are seeing that your natural response is somehow is been distributed. So natural response is available here. Okay, and these coefficients are dependent on initial condition, because this is based on initial value. Whereas the natural response are also available in this portion, but these coefficients are not dependent on the initial condition. Okay, so if you now just sum those two matrices, then eventually we'll have our solution of the state matrix, that is xt equal to phi t x0 plus 0 to t phi t minus tau d u tau d tau. Okay, so you just add those two, then you're going to get 2 okay, so if you just add those two matrices that we have obtained, okay, so just do a bit of calculation. Eventually, it will give you the final response, that is 1 by 8 plus 7 by 4 e to the power minus twice t minus 7 by 8 e to the power minus 4t and minus 7 by 2 e to the power minus twice t plus 7 by 2 e to the power minus 4t. Okay, so this is your required solution and this is your answer. And now the thing that we're saying that there are alternative approach of finding the state transition matrix. That is your example 4.13. So again, we have to find the same matrix. So Si minus A you have to find out. And that is, we already derived S minus 1, 8, S plus 6. So now we have to find out the inverse of this one. So basically Si minus A, we have to find out inverse. So that is basically the adjacent of Si minus A and the determinant of Si minus A. That will be adjacent coefficients are easy. So the coefficient of this one is this and the sign will be plus. So S plus 6. The coefficient of this one will be this one with a negative sign, of course, and then you have transpose as well. So minus 8. Then you will have 1 and then you will have S. So just figure it out. And then you have the determinant we already figured out in the last problem. So S square plus 6S plus 8. So we actually have something like this. S plus 6, 1 minus 1, 1 and minus 8. Then S. Then you have S plus 2 and S plus 4. So we know that we can write this one as S plus 6 divided by S plus 2 and S plus 4 and 1 by S plus 2, S plus 4. Then you have minus 8 by S plus 2, S plus 4. Then you have S by S plus 2, S plus 4. Okay, so this is your inverse matrix. Now we know that you have to take the inverse Laplace. Actually, you can also do the partial fraction thing here. Okay, so after doing the partial fraction, we can write this first parameter as a summation of S by 2 plus 1 by S plus 4. Based on your values of coefficients, we can see actually this is 2 and this is minus 1. Then we can see this one as S by 2 half and minus half S plus 4. And then we have here is minus 4 S divided by S by S plus 2 and plus 4 S plus 4. Then minus 1 S plus 2 plus 2 S plus 4. So this is your matrix, inverse matrix that we have, that is Si minus A inverse. And then if we just take the inverse Laplace transformation on that one, Si minus A inverse, then what we are going to see is same thing as the previously, same thing as previously, whatever we have seen, that is 2 e to the power minus twice t minus e to the power minus 4t half e to the power minus twice t minus half e to the power minus 4t, then minus 4 e to the power minus twice t plus 4 e to the power minus 4t minus e to the power minus 2t plus 2 e to the power minus 4t. So basically the same state transition matrix. So we obtain in a different method. So rest of the problem is same as before. So we just try to use the same method. So assalamu alaikum.